What's up, everybody? In this video, we're going to cover USACO's 2021 January contest at the silver level. Problem number 2, no time to paint. Bessie has recently received a painting set, and she wants to paint the long fence at one end of her pasture. The fence consists of n consecutive 1 meter segments, where n is between 1 and 10 to the 5th. So we have up to 100,000 boards making up a fence. Bessie has 26 colors available, which she labels with the letters A through Z in increasing order of darkness, with A being very light up to Z being very dark. She can therefore describe the desired colors she wants to paint each fence segment as a length n string where each character is a letter. Fine, okay, so for example, if I wanted to paint this one color A and this one color C and this one color Z and this one color B, then I would just represent that with the string A, C, Z, B. If I have a long sequence of the same color, B, 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 then this is just going to be B, 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 so forth. Initially, all fence segments are uncolored. Bessie can color any contiguous range of segments with a single color in a single brush stroke, as long as she never paints a lighter color over a darker color. She can only paint dark colors over lighter colors. For example, an initially uncolored segment of length 4 can be colored as follows. Okay, so I could do B, B, B blank. So let's just start in the middle here for B, 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 and then just leave that one blank. Then can paint LL. Since L is later in the alphabet than B, I can paint the L over top of this B right here, and then initially paint this one color L, and I'll have BBLL. Finally, Q, LMNOQ. Q is later in the alphabet than both B and L, so Q could go over top of this one right here, and Q also could go over top of this one right here, leaving us with BQQL. That would take a total of 3 brush strokes, 1 to put down the 3 Bs, 1 to put down the 2 Ls, and 1 brush stroke to replace the 2 Qs in the middle. So when it says that Bessie can color any contiguous range of segments, that means that we can cover multiple of these planks with a single brush stroke, just provided that the color of paint that we're brushing over is either darker than what's currently on the fence or that that segment has never been colored before. Running short on time, Bessie thinks she may need to leave some consecutive range of fence segments unpainted. Currently, she is considering Q candidate ranges, where Q is between 1 and 10 to the 5th, each described by two integers, A and B, with one being between, with A and B both being between 1 and N, and A being smaller or equal to N, or A being smaller or equal to B. So basically, they both will be at least N, 1, they both will be at most N, and A will be either equal to B or less than B, giving the indices of the endpoints of range A, B of segments to be left unpainted. So let's kind of review that because it's a lot. First thing to point out there is we have 10 to the 5th boards, potentially. We also have 10 to the 5th queries. Now, immediately what should catch your attention is if I do 10 to the 5th boards, which means I've got that many boards going across my fence, and I have then 10 to the 5th queries, and each query requires me to go through my fence and make some observation, then I'm going to have 10 to the 5th times 10 to the 5th observations, which is 10 to the 10th, which is too big. We can't do that. So immediately just looking at these numbers, they're giving you a hint that we are going to have to do something that's going to allow us to do these queries instantly in constant time. So this is one of those ones where you'll have to do some pre-computing. There's no dynamic programming on this problem, so you don't have to worry about that, but we do have to do some pre-computing on this fence so that later, after we go through this fence, which is going to take 10 to the 5th, then we've recorded some sort of information that will allow us to do a query, because we'll have 10 to the 5th queries, will allow us to do a single query in constant time, essentially. What these queries are saying is Bessie's going to have a certain way she wants the fence painted. For example, A, B, B, C, C, B, A. And if we just kind of eyeball this, we could do A all the way across, and then we could do B from here to here, and we could do C from here to here. That would take 3 brush strokes. But Bessie is then going to leave a certain segment blank, and it must be blank. We cannot paint it, which would mean that one of the queries might be that we're going to have to not paint these 2 right here. And if we don't paint those 2 right there, now we can't do A all the way across anymore. Now what we would have to do is we would have to do A just here, and then B could paint over it, and then again A over here, and B would paint over it. And in this case, actually, that would take 4 brush strokes. So even though Bessie's trying to leave a certain segment in the middle uncolored, she's making more work for herself because then she's got to do 2 separate parts. So what we need to do is we need to find a way that we can analyze this fence ahead of time, A, B, B, C, C, B, A, such that later, if we were told that we're not going to color these two boards, we don't need to recompute both sides, but we can somehow look at something we've stored around this location and something we've stored around this location that will then tell us, ideally, how much paint did we need going up to that location, so that then we can figure out how much paint we would need if we didn't have to do that middle section. There's a pretty good algorithm for that. We'll go over that in a minute. Let's finish reading the question. For each candidate range, what is the minimum number of strokes needed to paint every fence segment outside those in the range with its desired color, while leaving all fence segments inside the range uncolored? So we must leave them blank, even if it means more brush strokes. Note that Bessie does not actually do any painting during this process, so the answers for each candidate range are independent. So these are, Bessie is considering leaving this blank, but we don't actually have to do any painting. Essentially, I think this is just a hint to let you know don't actually run the simulation and that we need to do some pre-computing. Input format arrives from the terminal on standard in, so it's just being typed into the console. The first line contains N and Q. Remember, N is the length of the fence, and Q is how many different ranges of fence we are going to consider to leave blank. The next line consists of a string of length N characters representing the desired color for each of the fence segment, minus, of course, whatever part that she decides to leave blank according to a query when we're considering these queries. The next Q lines each contain two space-separated integers, A and B, representing a candidate range to possibly leave unpainted. The output format comes to the console, so just print it to the screen. For each of the Q candidates, output the answer on a new line. All right, let's kind of run through this and then we'll talk about how we're going to do this. So 8 means the fence has a length of 8. 2 means there are two different candidate ranges we're going to consider leaving blank. The actual desired fence colors are going to be A, B, B, A, B, C, B. 5, 6, 7, 8. Okay, that makes more sense. So then if we leave 3 through 6 blank, that's going to be 3 through 6 here. Okay, now that makes more sense. This is why we always have to run through our sample data and make sure you test this before you start writing code, just to make sure there's no misunderstanding on the problem. So if I leave 3 through 6 blank, then I've got A and B, which is going to require 2 brush strokes, A and B. You could paint A over both and then paint B over A, or you could just do 2 separate strokes. Same thing's going to happen over here. You could paint B over both and then paint C over top, and that would be 1, 2, 3, 4 total strokes. The second one indicates leaving the candidate range 1 through 4 blank. Let's look at what that looks like. So it is possible that we'll have a side of the fence that's entirely unpainted. If 1 through 4 was left blank, then we would have to just do A, B, C, B. And they're saying that's 3 brush strokes. And yeah, sure, that's 3 brush strokes. We could do A over the entire thing, and then we could do B over these 3 boards, and we could do C on this one board here. And then we would have A, B, C, B. And we can paint, remember, B over A, and we can paint C over B. That would be a total of 1, 2, 3 brush strokes. And then that would be the answer here. So I'm going to pull up my blank page. This is going to take a minute. So we don't have, I mentioned, we don't have dynamic programming. We don't need to do anything like that, but we do need to do some pre-processing. I guess this is kind of dynamic programming. This is using the prefix sum concept. It's not too complicated, but that does fall into the category of dynamic programming. It's not a novel algorithm. It's one that is pretty well established. So prefix sum, prefix sum. Just to give a really quick overview of how prefix sums work. Let's say like I were to have the numbers 2, 4, 3, 1, 6, 8, 5, and just for right now, ignore this fence. Okay, so I've got these numbers, and let's say like I wanted to find the sum of a certain subset of these numbers. For example, I'm going to do queries where I want to add up these numbers right here, but then I'm also going to have a query that adds up maybe these numbers right here, and then a query that adds up these numbers right here. Now, we're adding a lot of the same numbers repeatedly. And in computer science in general, there's a rule where if you're doing the same thing more than once, there's probably a better way to do it. So that's essentially what we're looking for, is we're looking for a way, in this case, similar to the other one, how do we add up a sequence of numbers without actually adding the numbers? The way you do that is you start at 0, you make a running total. 0 plus 2 would be 2. 2 plus 4 would be 6. 6 and 3 is 9. 9 and 1 is 10. 10 and 6 is 16. 16 and 8 is 24. And 24 and 5 is 29. So what these numbers indicate is, starting from the beginning, how much have you added? So up to here, I've added a total of 2. Up to here, I've added a total of 6. Up to here, I've added a total of 9. Up to here, I've added a total of 10. Now, the reason why these numbers are important is then if I want to say, okay, I want to look at a subset of these numbers. Specifically, I want to add 3, 1, 6, and 8 together. 3 plus 1 plus 6 plus 8, which would give me, was that 18? 18. So I know that before adding the 3 and before adding the 1, 6, and 8, my total up to there was 6. After adding the 3, the 1, the 6, and the 8, I went from 6 up to 9, up to 10, up to 16, and up to 24. I ended at 24, which means the amount that these numbers caused me to change is 24 minus 6, which is 18. And that was the answer we got by adding those numbers. Reason why that works is because we know what it was before we did added these numbers. We know what it was after we added these numbers. So then that'll tell us how much total was added in that subset. So this is called a prefix sum. That's essentially what we're doing here. So the way we're going to approach this then is we need to calculate, as we work our way across, how much paint will it take, starting at the left side, to paint all of the boards up to a particular location. So for example, if I know that up to this location, it has taken me 2 paint strokes going from this side to this side, and then I know up to here at this location, it's taken me 3 paint strokes. Then if I were to say, okay, I'm not going to do this range from right here to right here, then later, without having to reanalyze this fence, I can go here and say, well, I know it takes 2 paint strokes to paint up to that location where I'm deciding I'm not going to paint. If on the other hand, later I have a query that says, okay, I want to paint up to this location, but then just not paint this board, then I'll know that painting up from here to here would have taken 3 brush strokes. And I don't actually have to re-look at the fence in order to determine that. So we're going to kind of eyeball this to get the answer and make sure that algorithm makes sense. And then I'll show you how to actually generate these numbers. So remember, these are the board numbers here: board 1, board 2, 3, these numbers down at the board, 4, 5, 6, 7, 8. Okay, so just eyeballing it, I would need at least 1 brush stroke to paint this board right here up to the A. So if I were to start before the A, I would say, okay, I need 0 brush strokes up to here. And then after the A, I'm up to 1 total brush stroke. After the B, I'm up to 2 total brush strokes. After this B, it is still 2 total brush strokes. And in fact, after this A, it is still 2 total brush strokes. Because remember, if I wanted to paint up to that location, up to this location right here, then I would be able to do that with 2 strokes. I have a single stroke A all the way across, and then a second stroke B, because I can paint B over top of A. So I'm still only at 2 brush strokes. After this A, still only at 2 brush strokes. Now, this B is different. I can't paint this B all the way across here and then have this A on top of it, because I can't paint A on top of B. And if I were to paint A all the way across like that, I can't paint B and then have this B over here benefit. So that's going to be 3 brush strokes to get up to that location. So I'm going to put a 3 there. 3. And then up to C, that's going to be a 4th brush stroke, but then still only 4 brush strokes to get up to that B. Now, what that is now allowing me to do is if I were to have a certain range that's not going to be painted, for example, let's say I was going to stop here and say I'm not going to paint this range right here, then I can look here and I can see it takes me 2 brush strokes to get up to this location, to this A right here. And then I don't need to go through again and calculate how many brush strokes it's going to take. Then in order to do the other side of the fence, we have to do the exact same thing in reverse. So going the other way, I have 0 brush strokes as of here. And then going to the left, I would need at least 1 brush stroke to get that B. I need a second brush stroke to get the C and the B, because I would have to have 1 for the B and 1 for the C. Still only 2 brush strokes after this B. Remember, we're going this way. Because I could do B over the whole entire thing and then C just over the middle right here. That gives me 2 total brush strokes so far. I have A here. That's going to require a 3rd brush stroke because I would need A, the B, and the C. Still 3 after here. This B is going to require a 4th brush stroke, and then still 4 brush strokes, and then still only 4 brush strokes because I can just paint the B's over top of the A's. So going the other way, how many brush strokes I need, that's how many it would take. So once again, kind of looking at this, if I were to have 3 through 6, I think was the first range. They said 3 through 6. If I don't paint 3 through 6, if I block this out, 3 through 6, like that, then I can look at my numbers here and see, okay, up to here, I used 2 brush strokes for the ABB, going from left to right. And then going from right to left up to here, I used 2 brush strokes for the B and the C. That totals 4 brush strokes, which was the answer to the first query with the 3 through 6. Let's pull that back up and verify that. The 3 through 6 query had an answer of 4. Next query was 1 through 4, and they had an answer of 3. I'm going to back this up. So if I were to leave 1 through 4 blank, that would mean I'm not going to paint 1, 2, 3, or 4. Zone that out. So going from left to right, I have 0 brush strokes as of this location. So 0 brush strokes for the left side. The right side, I had 3 brush strokes up to that location, 0, 1, 2, 3, which means I'm going to have 0 plus 3, which is a total of 3 brush strokes, and that was how many they expected. So next question is, assuming we are in agreement and assuming that we understand that what I essentially need to do is do 2 versions of this pass. One is a left to right pass, one is a right to left pass. And then as of each board, I need to know how many strokes did it take total to get up to that board. So starting from 0, again, 1 stroke to get to this A, 2 strokes to get up to that first B, another 2 strokes to get up to that next B, still 2 strokes to get to that next B, still 2 strokes to get that B, but then a 3rd stroke for this B right here. Sorry, this is an A, not a B. A 4th stroke for that C right here, and still only 4 strokes for that B. So where do these numbers come from? Whatever it is we do left to right, we can do the exact same thing right to left, so I'm not going to solve those separately. I'm going to get rid of this, and we'll just focus on how to do the left to right version. And then for the right to left, you can either mirror the string and put it in the same function, or you can make the for loop run backwards or whatever, but it's going to be the same process. In order to figure out how much paint we need, what we're going to use is going to be a stack. If you're not familiar with stacks, this is a great time to learn. Essentially, the way a stack works is when you put something on the stack, it always goes on the top, like plates. You can imagine maybe like when you're a kid, you have those plates that have like an airplane on it or something. When you have a plate with an image on it, it's my little airplane here. Okay, so if I've got an airplane, and then I want to put another plate directly on top of that, whatever that plate is, that's going to cover up whatever was on the plate underneath it. I'm only going to be able to see whatever's on the top plate. Also, I guess you could, but we don't grab out the plates that are underneath and make all the plates drop down. We only ever take the thing that's the top plate off. So if you imagine stacking plates, your new plate would go on the top of the stack. The top of the stack is the only thing you can see at any given time. When you take a plate away, you take the plate off the top of the stack. And from a coding standpoint, that's exactly how stacks work, and that's why we call them stacks. So here's what's going to happen. As we work our way from left to right, remember, we can put a dark color on top of a light color. So the stack, if you were to imagine our fence as being, I'm going to actually kind of draw another fence here. If you were to imagine our fence as being a bunch of board segments, let's say like this is like a top-down view. We're looking at, let me see, write all these numbers here. This is supposed to be A, B, B, A, B, C, and B. Okay, so we were looking top-down. Imagine that Farmer John is standing here facing towards the fence, and we're looking at the top of the fence. So when we paint, we're putting our layers on and then stacking on top of each other. So like, for example, if I wanted to paint A, I can paint A all the way from here to here, and that's like 1 layer of paint. Then if I were to put B, use a different color for fun here. If I were to put B, which is green paint, which is darker, on top, then I have both A and B on this board right here. But since the B is in front of the A, obscuring the A person standing here looking at the fence is just going to see the B and won't see the A underneath. And that's exactly what our stack is going to be mimicking, is the process of what paint is actually on the fence at any given point. So we start with 0 because there's no items in our stack and there are 0 coats of paint. And then we get to our first board. Our first board, which is the first letter, requires an A. Our stack is 0, which means that currently there's no paint on the fence because the stack represents the layers of paint on the fence. So we got to put layer A on the fence. That's that red paint. That means that we've used 1 layer of paint so far. Advancing to the B is not the thing that's on top of the stack. The B is a darker color than what is on top of the stack. Because B is a darker color, we are allowed to put B on top of A. So I would put B on top of my stack here, B. And that brings us up now to 2 coats of paint. And you can see that there are 2 coats of paint here. We have used 2 coats of paint. This is not, by the way, the size of the stack. This is how many times you've had to add something to the stack. we've had to go get 2 coats of paint. And we'll come back to that again in a moment here. Okay, so now we've done that B. We've got A and B on the stack. We've got 2 coats of paint so far. Continuing forward, B is the same letter as what's on top of the stack. So this is the front coat of paint, and we want B to be the front coat of paint. So that doesn't cost us anything, and we remain at 2. We still only have used 2 brush strokes to get up to here. A, now we have to switch back to A. Now A is a lighter color than B. What that means is that this is where B is going to stop. But it doesn't cost us any turns to stop putting paint at a location. It only costs us turns to start adding paint. So the B is going to come off the stack at no cost, and we are still going to be at 2 coats of paint. Continuing forward, A is on the top of the stack right here. So since the top of the stack is already A, that indicates the front coat of paint is already A. Since we want this one to be A, that doesn't cost us anything. A can continue here. Now we've gotten to a darker color. This is where B has to come back. Now, because I wasn't doing B as of here, and I want to begin doing B as of here, I need to add that to a stack, but that's also going to have a cost. And I'm going to have to keep a running total of these. Because I'm adding a new coat of paint, I am now up to 3 times I've had to add paint. Because remember, this isn't just the size of the stack. The size of the stack, and we don't really even concern ourselves with the size of a stack, just whether or not the stack is empty. But up to here, even though there are only 2 things in our stack, I have had to add to my stack a 3rd time now. And what we're looking at is how many times we have to go get paint and start putting paint, because that's ultimately what we're looking for, is how many layers of paint there are. Okay, so we're up to 3. We're now advancing. This green paint is continuing over. The red paint's continuing over. But now we've hit C. C is not the same as what's on top of the stack. The top of our stack is currently a B. We want it to be C. I'll use blue for that. That's going to be a 3rd coat of paint. That's going to bring us up to 4 total times we've had to add paint to the fence. So now I've got A, B, and C on my stack. And again, I only have to worry about what's on the top of the stack because that's the color that would be visible, and that's the color I have to consider because I'm either going to paint on top of that front color or I'm going to discontinue that front color. Moving right along, we see the next color is B. The B is allowed to have the red here because again, we have red already on the stack anyway, so we might as well keep extending it. The green color for B is going to extend over, but that's the color we want. We don't want the blue. So the blue is going to have to stop here. And remember, stopping a paint doesn't cost anything. Only adding a paint costs something. So in order to have the paint stop there, we're going to remove the top of the stack. That's going to bring us down to B. Now that we're down to B, that matches what's going to be here. And then that's going to bring us up to still 4 coats of paint because I didn't have to add 1. What that did is that generated our numbers that we had originally up at the top here. 0, 1, 2, 2, 2, 2, 3, 4, 4, 0, 1, 2, 2, 2, 2, 3, 4, 4. So we did those a little out of order, but I wanted to demonstrate what we're going to do with the numbers before demonstrating how to generate the numbers. So you may want to rewind the video and watch that first part. But essentially, what's going to happen is heading back to our problem. We're going to take our original problem, A, B, B, A, B, C, B. We use our stack and we run through. Every time we add to the stack, we take 1 cost. So adding A to the stack is 1, adding B to the stack is 2. B is already on top of the stack. A is lighter, so we remove B from the stack, still only 2. A is on top of the stack now, so still only 2. B we have to add to the stack again, so that's going to move us up to a cost of 3. C we have to add to the top of the stack, it brings us up to 4. And then B, which is lighter than C, means we remove C from the stack, but still at 4 because we didn't have to add anything. Now it is possible we'll have to remove something from the stack and immediately add it. For example, if I had A, B, and F, and they said they wanted C, I can remove the F for free, but I still have to cost 1 to add the C on top. So that still would be an extra move. We will never need to add 2 paints on a single segment though. And there's never going to be a situation where, for example, if I had like A, and then F, and then C, there's not going to be any situation where we're going to want to add the C and the F on this board because we can always just add the F. We're going to have to stop the F anyway. We can add the F, stop the F, and then add the C. And that would be the same as adding both F and C here and then discontinuing the F. So we don't have to do anything fancy like that. It literally can just be processed left to right. You might want to draw a couple of these out to convince yourself that that's the case. Once we have these, Then when we get our candidate ranges, for example, this says we're not going to paint from 3 to 6. All we got to do is go to index 3 and see what that number is. And whatever that number is, that's how much paint it took to get up to index 3. You may have to watch out because, again, these are numbered from 1, not from 0. So be mindful of that as you're generating your code. If you finish up your code and you're getting the wrong number, or if it's off by 1, most likely it's going to be off by 1 on the right side, in which case you probably need to shift to the left one or to the right one to get to the correct index for whatever is in your array compared to what these segments are. Because remember, this is segment 1, segment 2, segment 3, segment 4. So when they say how much paint does it take to get up to segment 1, if we are going to paint segment 1, then we want to look at index 1. But if we were not going to paint segment 1, if we say I want to leave out segment 1, and that will be part of what we don't paint, then I need to look at index 0 of my array here to see how much paint it took to get up to segment 1, but then not to paint segment 1. So that's it. And then that's for the left side. You do the same thing going right from left, starting with B. So again, B goes on the stack, and then C goes on the stack, and so forth going this way. When you have your range again, whatever that number is, 6, that will be the index that we'll look at in the numbers we've generated going on this side for how much paint we need for the right side of the fence. Once you're done, you add the left and the right side of the fence, and essentially all that is 2 array lookups. You may want to watch this video a second time. This is a little bit tricky, but essentially that's the process. Add to the stack, keep track of how much paint it takes to get up to that part of the fence. Once you've generated those arrays, hang on to them, then just run through the query, pull the first number out of the first array when we went left to right, pull the second number out of the second array when we went right to left, add those numbers together, and that should be your answer. All righty, good luck coding it, and I'll talk to you on the next one.